I'm going to talk today about a result that I think is very exciting, related to a new mechanism to obtain superconductivity from repulsive interactions by a Skyrmion pair. And although this mechanism was inspired by studying twisted bilayer graphene, it only needs a few simple ingredients, which makes it likely to be relevant also to a wider class of system. So for the purpose of this talk, I will not really discuss the detailed aspects of whether this mechanism is applicable to twisted bilayer graphene. And instead, I will focus on a simple toy model related to twisted bilayer graphene, but ignoring some aspects of it, where we can establish to a large degree of certainty that this mechanism will be realized. So with this in mind, let me start by very briefly reviewing the experimental motivation behind this mechanism, which is twisted bilayer graphene, or TBG. So TBG is obtained by twisting two graphene layers relative to each other by some angle. And as a result, the result of this twisting is strongly modifying the band structure of the electrons by introducing something called the Maury pattern, which is a long wavelength pattern in real space. In particular, close to a certain angle known as the magic angle, we find that a pair of very narrow, almost flat bands appear close to Chern neutrality. And flatness of the bands means that the kinetic energy is quenched, which means that the interaction effects will be magnified. So as partial filling of these two bands, we expect enhanced correlation effects. And this is indeed what was seen in a remarkable experimental result by Pablo's group at MIT, where they considered the conductance of twisted bilayer graphene as a function of the filling of the flat band. So here they found two insulating dips, but these are in a sense relatively boring insulators. They arise from they can be understood within simple band structure, just because this flat band is separated by a finite gap from the remote bands. On the other hand, they also found two prominent dips at filling of -½ and +½ and these two dips cannot really be explained by single particle physics, so they have to be due to correlations. Furthermore, when they looked for superconductivity in the vicinity of this half-filling insulator, they found that there's two prominent superconducting domes flanking the correlated insulator. In the 2 years since then, several groups have reproduced these results. And one particular result that I want to highlight is from the group in Barcelona, where they saw not only clear insulating peaks at ±2, but also at Chern neutrality. And they also found superconductivity flanking this neutrality superconductor. So I won't go into the details of how these samples or these different systems differ from each other. It's still under debate, but I just want to show that we have signatures of correlated insulators and superconductivity, both close to half filling and to neutrality. So the first step to understanding the physics of this system is to study its non-interacting band structure, which maybe surprisingly turned out to have some very interesting and subtle topological features that has important implications of the physics. So let's start by zooming in on these two flat bands. So as we can see here, the two flat bands are not just featureless. There is actually some small dispersion, and more importantly, there's important features, which are these two Dirac cones connecting the two flat bands. A remarkable property of these two Dirac cones is that they have the same chirality. So this is different from standard graphene, where the two Dirac cones have opposite chirality. And this means that the bands have an unusual topology. And maybe the best way to understand this topology is to go to an alternative basis. This is a basis where instead of diagonalizing the band structure, so looking at the upper and lower bands, we look at an alternative basis where actually this dispersion is completely off diagonal. This may sound an unusual thing, like we usually don't. In most cases, we express our basis in terms of the energy eigenvalues, but we'll find that this basis actually very useful to understand the topology and also to understand the interaction problem. So here we see that when we go to this basis, this purely off-diagonal basis, that we have two flat bands that has opposite Chern numbers and that are related by this tunnel. And to understand the emergence of these Dirac cones in this alternative basis, there is a very simple argument by seeing that this tunneling creates actually an electron-hole pair between opposite Chern sectors. An electron-hole pair between opposite Chern sectors can be transformed into a Cooper pair in the same Chern sector if we simply perform a particle-hole transformation in one of the Chern sectors. But a Cooper pair in a Chern sector is like a Cooper pair, and a Chern band is like a Cooper pair in a magnetic field. And we know that a Cooper pair in a magnetic field has to admit some vortices. In fact, what happens is that the wave function of the Cooper pair in this system winds around the Brion zone by 4 pi, which means that it has to admit two vortices of the same vorticity, which precisely translate to these two Dirac cones with the same chirality. So if you are thinking about the twisted bilayer graphene, we actually have four-fold degeneracy coming from both the spin and valley degeneracy. So we have essentially 4 copies of this system. And to a good approximation, there's an SU4 symmetry that relates these 4 copies. In realistic graphene, this SU4 symmetry is broken by some terms, but I will not focus on this. So throughout my talk, I'll assume that this is a good symmetry. And this consideration motivates us to consider the following class of toy models that we now just forget about twisted bilayer graphene itself and just think of these toy models. So the toy model is to take several layers of tunnel coupled Chern bands. You can take n layers of tunnel coupled Chern bands that has opposite Chern number. So bands are pairwise coupled with opposite Chern numbers. And we make 2 main assumptions. The first is that we have an SUN flavor symmetry that allows us to rotate among these bands. And the second is that we have a repulsive interaction whose strength is much stronger than this tunneling amplitude. And this repulsive interaction, so in twisted bilayer graphene, this is taken to be Coulomb or screened Coulomb, but we can consider any repulsive interaction that has the same symmetries. And just to orient you on the relationship with twisted bilayer graphene, if we take the case of n equals 2, so we take only 2 bands in each sector, this essentially corresponds to a spinless version of twisted bilayer graphene, which is likely relevant to half filling, where one spin species is completely filled and all the action happens in the other spin species. And the n equals 4 case corresponds to the full twisted bilayer graphene case, which is likely relevant to the physics close to Chern.
So the first thing to try to understand about this problem is to just look at the infinite coupling limit. So switch off this tunneling. And in this case, we can relate this problem to a much simpler problem by just looking at one Chern sector. So one Chern sector in the simplest possible setting, n equals 2, is just a quantum Hall ferromagnet. So if we take a quantum Hall system that is spinful, we half fill it, and we have a repulsive interaction. The ground state is a ferromagnet. So the system spontaneously selects the spin direction that fills, and it fills it. And as it turns out, this argument can be generalized to our system. So if we have these two Chern sectors with any repulsive interaction. But of course, in this case, we will get a largely degenerate manifold of ground states. So first, we have to select a number of states to fill in the plus Chern sector, a number of states to fill in the minus Chern sector, such that the sum of them is equal to the total filling. And this would give us a state that has a Chern number n plus minus n minus. But then within each Chern sector, we also have a freedom because we can rotate these states among each other. And note that once we throw away this tunneling term, the flavor symmetry would be enhanced to SUN times SUN because we can rotate the flavors freely in this Chern sector or in that Chern sector. So this gives us some manifold of states. So in each Chern sector, we get a manifold that's equivalent to a Grassmannian. So we have the overall UN symmetry, but then we have to mod by the rotations that leave the filled states and empty states invariant. This is maybe too general, so let's consider a concrete example. So if we take n equals 2 at half filling, then we have 2 options. The first is to fill 2 bands on the same Chern sector, and then leave the other Chern sector empty. This gives us a state that has Chern number 2, and but this state is U2 times U2 invariant, so we just have a single state. We don't get a manifold. On the other hand, if we fill one state here and one state there, we get Chern number 0, but here we get a manifold state because we have the freedom to choose which state to fill here, and this freedom is parameterized by essentially a 3-dimensional unit vector. So this manifold is parameterized by 2 unit vectors. So the manifold is essentially a product of 2 spheres. For example, if we choose to fill the same state, then these 2 unit vectors are aligned. While if we choose to fill opposite states, then these 2 unit vectors are anti-aligned. Of course, this large degeneracy would be partially split once we include back the tunneling, which is what I will do next. So what happens when we add back the tunneling? My main assumption is that the tunneling is smaller than the interaction, so it can be understood perturbatively. And to understand it, we can consider these 3 representative examples. So in one of them, the tunneling connects to empty bands. So in this case, it doesn't have any effect. In the other case, it connects to full bands. Also, it doesn't have any effect because the electrons cannot tunnel. They have no place to tunnel. So it would only be relevant if I have a band that, or it will be maximized if I have a band that's completely full that's connected to a band that's completely empty. And in this case, I'm allowed to have some virtual tunneling processes where the electron goes and comes back and reduce the energy. And this energy can be actually calculated if I write an effective Hamiltonian for these particle hole pairs that are created by this tunneling. And so this energy splitting can be computed as this quantity, which is of the order of the tunneling amplitude square over the interaction scale. So let's see what this means for example, again, the simple case of n equals to a tap filling. So in this case, if we are looking at the same filling on both sides, filling the same band in both sides, so these aligned unit vectors, then the tunneling would be completely suppressed. While if we're looking at the opposite field states, then this tunneling would be completely functional and it would lead to an energy reduction, which means that this J term is essentially an antiferromagnetic coupling between the sectors. And this mechanism is essentially a band space analog of the super exchange mechanism that is known in the Hubbard model in real space. And what's also interesting about this system is that we have both a ferromagnetism, so we have ferromagnetism within the same Chern sector, but antiferromagnetism between Chern sectors. So far I've been just discussing the insulating states at integer filling, which is kind of the intro to my talk. The main thing I want to think about is superconductivity, which happens when I dope this system. And I will start by studying the simplest problem of n equals 2 first, before moving to the more complicated and general problem. So let me summarize what we know so far about this problem. So as I said, there is 3 Chern sectors, 0, +2, and -2. The +-2 Chern sectors are boring. There is no low energy degrees of freedom. And also they strongly break time reversal symmetry. So there's no chance of superconductivity there. The 0 Chern sector is labeled by 2 pseudo-spin vectors. And these pseudo-spin vectors have a tendency to order ferromagnetically within the same sector and antiferromagnetically between the Chern sectors. So I here introduce some stiffness that controls the tendency to magnetic ordering, and this will be controlled by the interaction scale. And this J is, as I said, is the tunneling scale squared over the interaction. So let us now see what happens if we add charge to this system. So we can again start by considering a very simple, like the simple example of just a single Chern sector. So this is just a quantum Hall ferromagnet. There's actually 2 ways to add charge to a quantum Hall ferromagnet. The simple way is to just add electrons, but this turns out not to be the best way. It's not the energetically cheapest way. Instead, an energetically cheaper way is to construct or to form a so-called Skyrmion texture. So here we have a ferromagnet, but then close to the center, we flip some of the spins and form a specific spin texture. This spin texture can be much more visible if we actually fold the plane into a sphere. In this case, it would look like this. And we can understand it as a texture where the spin vector winds around the sphere an integer number of times. And as it turns out, this texture carries a charge if it is in a Chern band. And this charge is equal to the number of times the spin winds times the Chern number. So what would this imply for our pair of Chern sectors, pair of tunnel coupled Chern sectors? Here, if we want to add a charge E, we have two options. Either we add it in the plus Chern sector as a skyrmion, or we add it in minus Chern sector as an anti-skyrmion. So an anti-skyrmion is obtained from a skyrmion by just flipping all the spins. Now note that these two would like to sit on top of each other because of this antiferromagnetic coupling. If we separate them away from each other, there would be, like, the spins would locally not be anti-aligned. So this term would not be happy. So we'll pay an energy to split them apart. Of course, you could say, well, this J is a small scale. We still have a Coulomb scale that's much larger that would want to pull them apart because they have the same charge. But it turns out that for a skyrmion texture, because the charge is distributed typically over a large area, we can make the skyrmions large enough so that this term, no matter how small, overcomes the Coulomb interaction. So essentially, we get a charge 2e bound state right away, which is, it's a very, like, remarkable result because we didn't really put anything by hand. We didn't put any interaction by hand, and we still got this charge 2e bound state that's essentially a Cooper pair. Of course, having a charge 2e bosonic bound state is not enough to get superconductivity. We still need to condense them. And to do this, we need to estimate their effective mass. There's a neat argument to do this, very, very visual. So we're thinking of a pair of skyrmion, anti-skyrmion, and we can think of this antiferromagnetic coupling simply as some spring that attaches them together. Let's see what happens when this object starts to move. So when this object moves with a certain velocity, these two objects, they have opposite charges. They have the same charge, but they experience opposite magnetic field. So they would experience opposite Lorentz force that would tend to pull them apart. On the other hand, there's this spring force that likes to bring them back together. And combining these two would give us an optimal separation for a moving skyrmion anti-skyrmion pair. And substituting this into the energy, we get an energy that's proportional to v squared over j, which means that this object essentially has a mass, as an inertial mass that's proportional to 1 over j. And from this, we can read off the condensation temperature, which is proportional to this j scale, and also is proportional to the density of these skyrmions. Here, AM is just a Morey area. It's just for dimensional reasons.
Eslam, can I ask a quick question?
Yeah.
Is it like, so if I were to think of these skyrmions, can I think of them as like states that are occupied by one electron? Like, do they have other occupancy states, or is it always that they don't exist unless they have a single electron in them?
Well, they are smoothly connected to a state which have a single electron.
Okay, but you can't. So I can't tunnel a second electron to the same skyrmion.
I mean, they have an overlap with. So it's a multi-particle state, so it could have an overlap with other multi-particle states. But it's smoothly, if you shrink it smoothly, you would get it's a single electron.
Okay. And then just real briefly, so this 2e state, the way you're counting it, does this have 2 electrons in it, or is one total electron? It does?
No,
okay.
2 electrons. Yeah.
Okay, great. Thank you.
So actually, the order parameter you get from this is it's smoothly connected to the VCS order parameter. It's not some exotic type of order parameter, but the mechanism itself is exotic. And so what we've established here is essentially a way to get superconductivity from strong repulsive interaction, just based on a very few simple ingredients. We didn't really need to invoke relaxation, retardation. We didn't need to invoke screening, and we really didn't need to do any tuning. So it just comes out naturally.
So can I just say something? Just to clarify, I think the right way to think about it is that this has 2 extra electrons. Of course, there are a lot of electrons. It's half filled. The band is half filled, and there's a gap. And now you in the skyrmion situation, you still have a gap between the excited states and the the filled states and the unfilled states, but there happen to be two more electrons in it than there would have been if there wasn't the skyrmion there, and that gives you your charge 2e.
Yeah, thank you. That was yeah, that was basically my question about how to get that counting. Thank you. Yeah.
Sorry, I had some problem with the sound.
Can I continue? Can someone speak? I
Yeah.
think I had some problem with the sound. Okay, okay.
Continue.
Yeah, thank you. Thank you for the comment. But yeah, so I agree with what you said, that so we have a large number of electrons and we're just looking at the extra electron added on top of that. So I mean, so far in the talk I've focused on this very intuitive pictorial way, but to establish this more rigorously would need to do much more serious calculations, which is what I will do for the rest of the talk. So the rest of the talk will be a bit more technical, so feel free to stop me at any point if something is unclear. So to understand this mechanism, I will write some field theory to describe these skyrmions. So the starting point is again a quantum Hall ferromagnetism. So a field theory for the quantum Hall ferromagnet was written a long time ago. And it has a few simple ingredients. So this first term is a very phase term that just captures the fact that the skyrmions feel an effective magnetic field. The second term is just this gradient term. And the last term is the one that assigns charge to the skyrmion texture. So this delta rho is just the skyrmion topological density, but then it enters with opposite signs, plus or minus signs, depending on whether I'm in the plus Chern sector or the minus Chern sector. Then in addition to this, I need to couple the two Chern sectors, and there's two ways to do that. There's two ways the two are coupled. One is through this antiferromagnetic coupling, and the other is through Coulomb interaction. So because the Coulomb interaction is coupled to the total density, to the total charge density. Now, if we're looking at energies that are small compared to this J scale, we can essentially think of these two spin or pseudo spins as antiferromagnetically locked and integrate out the ferromagnetic fluctuations. So when we do this, two things happen. First, instead of a linear time derivative term, we get a quadratic term. So this linear term cancels, and we get instead a quadratic term whose prefactor is proportional to 1 over j. This is essentially an indication that the skyrmions of this new manifold don't feel a net magnetic field. And second, this chemical potential term now has twice the prefactor. So instead of 1 over 8 pi, we have 1 over 4 pi. What this means is the following. The skyrmions we're looking at now are skyrmions of this antiferromagnetically locked manifold. So when I form a skyrmion in one sector, it automatically comes with an anti-skyrmion in another sector. So the skyrmions of this new n vector are precisely the charge 2e bound state of skyrmions I showed earlier. So this model has charge 2e skyrmions. Like the simplest skyrmion has charge 2e. So to proceed further, I need to have a theory that allows me to consider a phase where this vector n is disordered. So this was derived for the deep inside the insulator, but I need to be able to go outside the insulator and probe the superconductor. And a very convenient way to do this is a so-called CP1 representation or CP1 model. So this introduces a complex two-component vector that is it's two-component unit vector, so it has a magnitude 1. And we can write n, the vector in terms of the 3D unit vector in terms of this. But of course, this object is complex, so it has 4 components. This is a constraint, so there's 3 free components here, but there's only 2 free components here. So there's a gauge redundancy in this description, and this gauge redundancy corresponds to the overall phase of Z. This doesn't affect n. So this gauge redundancy would be captured in the field theory by introducing some U1 gauge field. So this would be a dynamical gauge field. When we introduce it, it's tied to Z, but we expect at low energy that these two would be decoupled. And anyway, the low energy theory reproduces this constraint. So we don't need to enforce it. But the important thing is that the skyrmion density in this language is just expressed as a flux of A. So a skyrmion would be just a 2 pi flux of A. And in terms of these variables, we can rewrite the theory. So we have, so the kinetic term becomes this kinetic term of the Z field minimally coupled to this U1 gauge field. And coupling to the chemical potential takes the form of a mutual Chern-Simons term. Two important things to note here. So I here replaced the chemical potential with just a background gauge field. So it's zeroth or time-like component is the chemical potential. And you see here that there's this prefactor of 2, which precisely captures the fact that a 2 pi flux of A carries a charge of 2 under the background field. I also introduced some momentum cut of lambda that is related to the lattice scale physics. And I defined this coupling constant G, which is related to the antiferromagnetic coupling and the stiffness. So we can, since this stiffness is controlled by Coulomb scale, we can actually write this as a ratio of H over Coulomb. So crucially, the coupling of this new theory is 1 over the coupling of the old theory. So let's now try to understand the different phases of this theory. So again, I'm writing the Lagrangian here. So at small values of G, we expect that this Z boson to be ordered. So we have some finite expectation value of Z. And since it's minimally coupled to A, this would take A. And we just have this term would not be very effective. So this is essentially the ordered phase. It's just a complicated way to express this phase where this n vector is ordered. However, a more interesting thing that is enabled that we can access using this theory is a disordered phase. So if we take the expectation value of Z to be 0, so Z is gapped, we'll find that the A will be in the Coulomb phase. And we can actually integrate A out to get a dual theory of a boson that is coupled to the background electromagnetic field with charge 2. So this is essentially a theory that describes the superconductor. To connect this to the Skyrmion picture, let me again reiterate what I said earlier is that the Skyrmions are essentially the operators that create a 2 pi flux of this dynamical gauge field A, so the so-called monopole operators. So from this mutual Chern-Simons term, we can see that they carry charge 2e. But an important thing is Skyrmions are finite energy excitations of the theory. So if I just insert a 2 pi flux here, I would actually get a logarithmically divergent term. So the Skyrmions have to be accompanied with a phase winding of this Z variable. Since this Z has 2 components that both couple to A, so both of these components have to wind. So this tells us that if we condense this Skyrmion operator, it will disorder the phase of Z1 and Z2, but it doesn't necessarily disorder the phase of the Z1 dagger Z2 or Z1 star Z2, which essentially tells us that we don't really have to destroy the insulator to get a superconductor. We can just give this Z1, Z2 a 0 expectation value, but maintain a finite expectation value for Z1 star Z2. And this is precisely related to the spin order parameter. And one maybe simple way to understand it is that you can see that this Skyrmion texture only deforms the spin close to the core, while away the spins keep ordered. So essentially, including many of these Skyrmion textures don't necessarily disorder the background. So using this picture, we can propose some schematic phase diagram. So here we change this coupling G, and here we change the chemical potential. And we are starting here in deep inside the insulator for small values of G. And there's essentially 2 ways to get into the superconductor. One of them is through doping, which is, in a sense, the physically easier one to control. What would happen is that at some critical chemical potential that is equal to the Skyrmion energy, we start to introduce Skyrmions in the system. And they immediately condense, giving you a superconductor, but this doesn't destroy the insulator. So we get a coexistence phase of the superconductor and the insulator. On the other hand, we could also try to go out of the insulator by weakening this, by changing this coupling. And it turns out that this is a well-studied transition called the deconfined quantum critical point that was studied in 2D quantum magnets. And the interesting thing about this transition is that it's a transition between a direct second order transition between 2 ordered phases. So it doesn't fit into the standard Landau paradigm of symmetry breaking. And we can simply understand it by that when we go through this transition, we not just condense the skyrmions, which are associated with pairs of these, but we condense individual vortices, so half skyrmions. So to go beyond this schematic phase diagram and make some quantitative statements about the superconductor, we would want to employ some large N approximation of the CP1 model. And I wouldn't go into the details of the calculation, but I'll just show you the results. So here I'm showing this density of the skyrmions as a function of the coupling G and the chemical potential mu. So what you can see here is that we are here inside the insulator, and once we hit a certain critical chemical potential, we start to introduce a finite density of skyrmions in the system. And actually, this phase separation line can be obtained analytically, and it's in the limit of small g, it's just 4 pi rho, which is known as the elastic energy of our skyrmion. We can also compute the phase stiffness of the superconductor, and it turns out that this becomes finite once we start introducing skyrmions in the system. So skyrmions immediately condense when we put them in the system. And one way to see this is to translate it into more physical units by computing the TC that comes out of this. And we find that TC is given by this simple expression, at least to leading order in the doping. So it's proportional to J, the antiferromagnetic coupling, and to the doping mu. And if we take n equals 2, we can actually produce some figure of TC as a function of doping. And if we use the scales from TVG, we get something around 1 to 2 Kelvin. So it's the right scale of physics in twisted bilayer, of superconductivity in twisted bilayer. In addition to this field theory analysis, this mechanism has also been observed numerically in a toy model. So in a very nice work by Mike Zalatov's group, they considered this toy model. So they took 2 quantum Hall systems in opposite magnetic fields, added the Coulomb interaction and an antiferromagnetic coupling. And the extra ingredient they have is this easy plane anisotropy. So they added some easy plane anisotropy. This is actually relevant for the actual TBG. So these anisotropy terms that violate this flavor SU4 rotation symmetry that I neglected earlier. And what they've seen is the following. So they see some superconductivity, and it turns out this anisotropy term is bad for superconductivity, but as it goes to 0, you get superconductivity no matter how small J is. So J could be much, much smaller than the interaction, than the Coulomb interaction scale, and you could still get superconductivity in this system. Furthermore, when they computed the pair energy just from the nonlinear sigma model numerically, they found that this superconducting pairing and the pair energy obtained from the skyrmion picture match pretty well, which provides good evidence that the skyrmions are the ones leading to this mechanism, the skyrmion pairing. So having worked out the simplest case in detail, let's move to the more complicated case of n equals 4. So besides being relevant to twisted bilayer graphene at neutrality, this case turned out to have some very interesting new features that are not present in the simplest n equals 2 case. So before discussing the skyrmions in this picture, let me first discuss some broad considerations on symmetry, transformations of the superconductors for the SU4 case. So we start with some BTS pairing function, and we are assuming we're talking about a superconductor that can at least be smoothly connected to the BTS superconductor. So here alpha and beta are just some generic indices. They can contain momentum, or they can contain like all orbital indices. And if these C of alpha transform under a global symmetry by some unitary, then this delta will transform by the unitary and the unitary transpose. Note that this is different from the way a particle hole operator transforms, which would be UU dagger, which means that the action of U on this pairing is not the adjoint action. For the SU2 case, this means that we can decompose this action into the very well-known singlet and triplet channels. But if you have SUN, where n is larger than 2, you don't get a singlet channel. So for example, for SU4, this action decomposes into a 6-dimensional and a 10-dimensional irrep. So these are essentially the anti-symmetric tensor representation and the symmetric tensor representation. So this has important implications for the physics because this superconductor necessarily breaks the SU4 symmetry. So it's impossible to have a finite temperature, even in the BKT sense. And it has nice, interesting implications for TBG that we discuss in the paper that should appear later this week. But for the purpose of this talk, I'm focusing more on the Skyrmion aspects of the superconductivity, so I will not discuss the physical implications of this step further. But one implication is that this is a charge 2e superconductor. So there is another possibility that maintains this SU4 symmetry, which is to take a superconductor form that is a charge 4e superconductor. So we take a condensate consisting of 4 fermion operators. In this case, if we take this pairing function to be proportional to the antisymmetric tensor, we can show that that under this transformation, delta changes by the determinant of u, and if u is in SU4, then delta is invariant. So we can get a singlet superconductor, but it has to be charged 4e. So how can I understand these two possibilities from this Skyrmion picture? So in this n equals 4 case, what we have is 2 Chern sectors where we fill 2 out of 4 bands in each sector. And first, just to establish that Skyrmions are possible in this system, let me just state that this manifold is some Graphenian manifold, U4 over U2 times U2, which means that the second homotopy group is V, and this is what tells us that it can admit Skyrmion textures. So Skyrmion textures are mapped from the sphere to the manifold. So this tells us that there is a possibility of Skyrmions in the system. And there is actually an easy way to understand the simplest Skyrmion. So if we want to have a charge E Skyrmion, we just take one of the filled bands and one of the empty bands and think of this as a 2-level system where we form Skyrmion. So this is essentially the same as the n equals 2 Skyrmion. So it was at charge E. But of course, because we had to make a special choice, this would have some non-trivial transformation properties under SU4, which I will discuss later. Instead, we can take a more symmetric combination. So we take 2 of the bands and then form a Skyrmion with the other 2 bands. So this would essentially be like 2 copies of this Skyrmion. And in this case, we get a charge 2e Skyrmion in each sector. Then we have 2 possibilities. So if we pair the charge e Skyrmions, we get a charge 2e superconductor that will break the symmetry. If we pair the charge 2e Skyrmions, we get a charge 4e superconductor that could be a singlet. And what I will show you now is that I will derive a field theory that establishes that this is indeed the case. So in the n equals 2 case, we derive this field theory starting from the quantum Hall ferromagnetism nonlinear sigma model. We can also do the same here, but there's actually a simpler way to do this derivation. And this simpler way is to use some Parton construction. So I will first review this Parton construction for the n equals 2 case before considering this more complicated case. So here we are filling 1 band out of 2 in each Chern sector. So we're looking at some spinful fermion that we can decompose into a spinless fermion that carries the charge and a bosonic spinor that in a sense carries the spin. So this Z would essentially describe the wave functions of the filled band in this space of 2 bands. This description has a gauge redundancy because we can rotate the phase of Z by some angle phi and rotate the phase of F by the opposite angle, which means the field theory would have effectively 2 emergent U1 gauge fields for each Chern sector. And we can write some Lagrangian by integrating out this fermion fields. So this is essentially the simplest generic Lagrangian we can write. The important feature of this Lagrangian is that because this fermion couples both to the background gauge field and to the dynamical gauge field, so we get this type of Chern-Simons term that contains both. And we also have this plus-minus term because of the opposite Chern sectors. So the next step, and also we have added here a potential that controls the expectation value of this D field. So the next step is to couple these sectors. So as I said earlier, this coupling would would make these sectors antiferromagnetically coupled. But what does it mean in terms of the z variables? It actually means that these z variables are orthogonal. So antiferromagnetic coupling means if we fill the state, we leave it here empty. So if this is like 0, 1, this will be 1, 0. And we can rewrite this term that selects for this condition for the antiferromagnetic coupling using some identity, some fierce identity, as a condition of maximizing the determinant of a certain matrix. This is just a matrix that it's a 2 by 2 matrix because this is the two component column vector and this is a 2 component column vector. So we get a 2 by 2 matrix. And the condition of maximizing this determinant is precisely the condition that these two are orthogonal if we are fixing their norm. But what is the implications of this? We have this term with a minus prefactor, so it will want to condense this field, this bosonic field. But this bosonic field couples to the sum of the two gauge fields, A plus and A minus, because essentially this determinant is proportional to Z plus times Z minus. And this means that when this develops an expectation value, this combination A plus plus A minus would develop a gap, and it would be Higgs. So we can, for low energies, we can just restrict ourselves to A plus equals to minus A minus, which means essentially we can just eliminate one of these dynamical U1 gauge fields. And using this condition, we can also eliminate one of these Z variables. So eventually we get the same theory that we had before. We have just a single Z variable, a two component Z variable coupled to a U1 gauge field and with a mutual Chern-Simons term. So when we enforce this condition, so if you recall here, this one has the ADA term, but it comes with opposite signs from the two Chern sectors. So when we substitute A plus equals to minus A minus, they cancel out. But the mutual term doesn't cancel, it adds. So you get this factor of 2. So let's now see how this generalizes to the n equals 4 case. So in this case, we are filling 2 out of 4 bands in each Chern sector. And the Parton, we can do a very similar Parton decomposition. So now this is an operator that has 4 components. It's a fermion that has 4 components, and we write it in terms of our 2-component fermions that describe these 2 filled bands. And they're related by a bosonic object that is a 4 by 2 matrix. So this representation has a larger gauge redundancy. It actually has a U2 times U2 gauge redundancy. So for each Z, we can act with U2 gauge symmetry on the right and act with its conjugate on the fermion. In addition, the global symmetry acts on these Z variables by less multiplication. So F is invariant under the global symmetry, but Z has both a charge under the global symmetry and the gauge symmetry. But F carries the background charge. So this theory would have actually, so U2 can be decomposed into a U1 and a SU2. So this theory has 2 U1 gauge fields and 2 SU2 gauge fields. So 2 non-abelian SU2 gauge fields. And the Lagrangian has the following form. If we integrate out the fermions, what we would get is, this is the same abelian Chern-Simons term I got before, but with an extra prefactor of 2, because we have 2 fermions in each Chern sector. But we also get, in addition, a non-abelian Chern-Simons term that has opposite levels in the 2 opposite Chern sectors. And note here that this gauge field couples to Z by right multiplication, just because Z is 4 by 2 and the gauge field is a 2 by 2 matrix. So the next step is to couple these 2 sectors. And I will do the same as earlier. I will add this term to the action, which maximizes the determinant of this matrix that tries to make this Z plus and Z minus orthogonal. Of course, now Z plus and Z minus are 4 by 2 matrices. So if I put them next to each other, I get a 4 by 4 matrix. And the way they couple, so now we can see what happens when we condense this. The way it couples to the abelian gauge field is like this. So it's very similar to before, but it has this extra factor of 2. And the reason is that phi is quartic in these. So it has 2 factors of Z plus and 2 factors of Z minus. This means that when we condense phi, we don't completely Higgs out A plus plus A minus. Instead, we Higgs them modulo a Z2 gauge field. So we can get rid of this A plus A minus by introducing a U1 gauge field plus a Z2 gauge field. And then the full Lagrangian has the following form. So this mutual Chern-Simons term now has a prefactor of 4, which is important. So in the previous case, it has a prefactor of 2. Now it has 4. And we also get this extra mutual Chern-Simons term between this Z2 gauge field and the U1 gauge field. And unlike in the CP1 case, we cannot really eliminate one of the Z1s in terms of the other. So we have to keep both variables. But because of time reversal symmetry, we will assume that the potential that gives them expectation value is the same. So they either condense together or uncondense together. So let's now see what are the phases of this field. So the simplest phase is an insulator. So in this phase, we just condense this Z plus and Z minus. Again, this is kind of a very complicated way to express the insulator. And this would Higgs all the gauge fields. But the interesting thing to see in this phase is what are the finite energy excitations. So we want to be able to see the charge 2e skyrmions and the charge 4e skyrmions in this theory, and hopefully understand their transformation properties. So the first finite energy excitation we can consider is a 2pi flux of small a. This, of course, will be associated with some phase winding of this Z plus and Z minus. But due to this term, which has a prefactor of 4, this object will have a charge of 4e under the background field. So this is actually the charge 4e skyrmion. So what about the charge 2e skyrmion? The charge 2e skyrmion is more tricky to see. But one way to see it is the following. We first split this Z plus, for example, into 2 4-component column vectors, Z1 and Z2, and consider like the abelian limit of this A field, so just proportional to sigma Z. And when we do this, this kinetic term looks like this. So A plus AZ couples to Z1 and A minus AZ couples to Z2. So for the 2pi flux in A, we had the 2pi here, so Z1 had to wind by 2pi and Z2 had to wind by 2pi. However, now we have another possibility, which is to put pi here, which would give us 2pi in this one and 0 in this one. So we can get a well-defined finite energy excitation by putting the pi flux in A and a pi flux in AZ, plus some phase winding in this Z1. This leads to the following identification. We can think of the charge 2e skyrmion as a pi flux in small a pi flux in A plus, and a pi flux in A minus. Because if we insert a pi flux in A, we have to insert a pi flux in both A plus and A minus. However, there's a problem. This object is not really gauge invariant. The reason is that these non-abelian Chern-Simons terms give a gauge charge to the pi flux in A plus and A minus. Actually, what it does is that it forces the pi flux of A to carry a fundamental representation under the SU2 gauge field. This means that we have to attach some operators to these monopole operators to finally realize the gauge invariant operator. And since this Z plus and Z minus also transform as a fundamental representation of the gauge group, we can just attach one Z plus and one Z minus. And the interesting thing when we do this is that this gives us the symmetry transformation properties of this object for free, essentially. So here I choose to contract this plus and Z minus with some generic matrix, gamma. So this matrix is a 4x4 matrix. And it turns out if I choose this to be an antisymmetric matrix, then this operator will transform as a 6-dimensional representation of SU4, the 6-dimensional tensor representation of SU4. And if it's symmetric, it transforms as a 10-dimensional representation. So this is exactly the two possibilities we find for the symmetry representations of a charge 2e object. So this object matches exactly the quantum numbers we expect for a charge 2e skyrmion, for a charge 2e Cooper pair. So now it's kind of easy to see, or maybe not very easy to see, what are the different superconductors. So to get the charge 2e skyrmion, we need to gap out or uncondense this Z plus minus variable, but leave this combination condensed. This will not Higgs out all the gauge fields. So this would only Higgs out some combination of these non-abelian gauge fields, but the remaining would be unhiggs. And we can show that this is really equivalent to the condensation of the Skyrmion operator that I showed you earlier. Maybe this is too much detail. Yeah. For the charged 4e superconductor, this is just obtained by gapping out all the z variables. So this also is equivalent to the condensation of this just 4 pi Skyrmion. And essentially all the gauge fields are now on Higgs, and this gives us the right properties of the charge 4e superconductor. So this suggests the following schematic phase diagram. First, let me define this new field that is V transpose Z, and gamma A denotes some generator of the SU4 group that I will take to be in the antisymmetric representation. This turns out to be the one that is actually favored by the antiferromagnetic coupling. So we'll consider this as an independent field that can be independently condensed. And let's see what phase diagram we can get. So for the insulator, it turns out that we can get not one, but 2 possible insulators. So we are condensing this Z plus minus, but also this phi variable, so giving them non-vanishing excitation value. But there's 2 ways we can do this. We can do it in a way where the expectation value of phi is kind of tied to the expectation value of Z, or we can do it such that they're kind of independent, so their magnitudes are not related. This one is the insulator I have been talking about for most of the talk, so it has a U2 times U2 symmetry. But this is also a possible insulator that has a lower symmetry. And it's actually important to keep it to understand this full phase diagram. Now let's see where the superconductors lie. And so the charge 4e and the charge 2e superconductor can be seen here. And for the charge 4e superconductor, this z variable and the phi variable are just uncondensed. So this relationship is automatically satisfied, which means as we cross this boundary, nothing happens to this relationship, and just what we have is uncondensing z. On the other hand, here, what happens is that also this relationship remains unsatisfied and or remains satisfied, and what happens is we uncondense z. So as we cross this boundary, we just uncondense z. As we cross this boundary, we just violate this relationship. And as it turns out that these transitions are Landau transitions. So the red line denotes a Landau transition. This phase always has a larger symmetry than this phase, while these lines are non-Landau transitions. So these 2 phases have different patterns of symmetry breaking. So in the last maybe 5 minutes of my talk, I'll just speculate on what could be the possible symmetries of these lines. Of course, at the phase transition, the symmetry group has to incorporate both the symmetry group on the right and the symmetry group on the left, but it could be much larger. So in the case of the SO5, the standard deconfined quantum critical point, we actually get an enlarged SO5 symmetry. And what I will speculate now is about this point, whether actually we can guess the enlarged symmetry of this point. And to do this, let's see how do we usually do this for the deconfined quantum critical point, the SO5 deconfined quantum critical point that we understand. Usually the way to understand it is to combine the order parameter of the insulator and the superconductor in a single object. This would be a 5-component object. And consider some Dirac theory. So this Dirac theory, these both would act as a mass for the Dirac theory. And essentially in the Dirac theory, they both enter in the same way. So we have this mass that corresponds to a 5-component vector, which means it lives on the S4. And what indicates that we have a deconfined quantum critical point is the existence of a certain type of topological term, so a Weiss-Zumino-Witten term. This indicates that the only way we can get an SO5 symmetric theory is if it is gapless. So now let's see, is there a way to generalize this? And in fact, there is. If we select a specific superconducting channel, it's actually the one that is favored in this Dirac picture. what we find is that the proper generalization of this manifold is actually some symplectic Grassmannian manifold. And as a check, let's check just the simplest case, the SO5 case, to see if everything checks. So when n equals 2, this manifold indeed is a sphere, is a 4 sphere, S4. And the total symmetry of this theory, the SO5, is the same as SP4. The two symmetries also match. So for the n equals 4, this favored pairing is actually correspond to this 6-dimensional area. And the manifold is a complicated object, is this SP8 over SP4, SP4. However, it has the topology that allows you to add a weight to mean weight term. It has pi4 equals to z. And essentially, a weight to mean weight term is related to a mapping between the 4 sphere and the manifold. So if we have a pi4 equals to z, it means we can add a weight to mean weight term. This suggests that there is a theory that connects this charge 2e superconductor to the insulator that has an enhanced, a deconfined quantum critical point with an SP8 symmetry. And then this would suggest that this theory describes this critical point. But this is, of course, a bit speculative, so we would need to check more for like matching of some of the operators and the anomalies of these theories. So this is the end of my talk, and let me finish by acknowledging my collaborators. So most of this work was, of course, with Ashwin Vishwanath at Harvard, but also some of the more recent work was with Patrick and Shang Liu, Patrick Levitt and Shang Liu at Harvard, but also the earlier work was in collaboration with Mike Zalato's group at Berkeley. So thank you for your attention.